Okay, the correct way to think about a determinant is as the area scaling factor for a transformation. So this is sort of the nice way to think about it. It's so i.e. a given transformation T from n-dimensional real space to n-dimensional real space, defined by a matrix, right? T of x equals ax, a times x, where A is an n by n matrix, then the determinant of A is the area or volume, I guess area, I'm thinking the two-dimensional transformation. Volume with three-dimensional, there's higher dimensional versions of volume, like called hypervolumes. It's the area volume, area slash volume scaling factor. Get that a little better. For T, meaning that if I have some object, like say like a triangle in the plane, and I apply T to the whole plane, then the area of the triangle will be scaled by some number, and that number is the determinant of A. Right, okay, so that's kind of the right way to think about the determinant. It's actually this very fundamental way. We'll see later why it's very helpful. But it's also helpful to think of it as not just an area scaling factor, but as an actual area. So because we saw in the we've seen in examples that if we take sort of, just the regular XY plane and we apply some transformation to that, and we get the plane back, and if we start with, a 1-by-1 box, right? That's sort of, if there's I is there and J is right there, then we somehow, if we get, because it's scaling, this is area 1, right? And if this is what happens to I and this is what happens to J, then we get this parallelogram that they form. And the area of this is the determinant of A. So in fact, I can think of, if I want, if A is, let's just think about the 2-by-2 case for a second. If A is this matrix with columns AC and BD, then we know T of I is AC, T of J is B comma D. And so we could also think of it as just, the determinant is just the area of the parallelogram formed by AC and BD, where this is a signed area. It's right. It's a as we've talked about, it's a signed area where it depends on the sort of relative position of the columns. If you here, you go sort of counterclockwise from AC to BD, just like it started when you go on the left from I to J is counterclockwise. So in that case, you get a positive area. But if that relationship was flipped, it's called the orientation, was flipped, you'd get a negative area. And so in fact, I want to think of the determinant a slightly different way. I want to think about it in terms of just the area or volume given a matrix. I'm kind of forget the transformation perspective for a minute. So if A has columns, let's think it's a V1, it's an n by n matrix. If it has columns let's call them C for column C1, C2 through Cn, then we can also think of determinant of A, the determinant of A as sort of the volume, the area or the volume of formed by these vectors in space, in the plane, in space, or whatever. So like, you know, we've talked about if you have three vectors that they form a parallelepiped in space, if you have two vectors that form a parallelogram. And so the determinant is that number, right? And what I really want to talk about is, so I want to think about the determinant that way just for this video. And in particular, if we think about the determinant this way, it'll help us derive some properties that will be very useful later on. So let's actually think about this. So let's just look at the 2x2 case. So I want A to be the matrix with columns V1. Oops. Oh my God, I changed it to V. Sorry, I just used the wrong letter for these. Let me, these should all be C's, I guess. Sorry about that. That should be C1 through Cn. In my head, I was thinking V for some reason. So C1, C2 through Cn. And this is C1 and C2, right? So those are column vectors, C for column. And so the determinant of A, the two-dimensional notion of volume is area. So it's the area formed by V1 and V2. And I want to think about some area properties. The area of the parallelogram formed by V1 and V2 is what we're talking about. So there's a bunch of properties of area which, you know, they don't. You might just have to think a little bit, or I might have to draw a picture. But the first property is that if one of the vectors is a zero vector, then the area is zero, right? The zero vector, you don't get a parallelogram. It's sort of a, we would say, a degenerate parallelogram, or there's really just no parallelogram at all. And so that's hopefully pretty clear. Along very similar lines, if we have the same vector repeated twice, which is the same column repeated twice, that's also gives us sort of no parallelogram at all. You know, up in the picture up here on the right, you'd have the same vector twice and they wouldn't make a parallelogram. So hopefully those are both pretty clear. But there's other interesting properties. Like, for example, what if I take one of the column vectors and I scale it by some scaling factors? So let's just say I scale it by A. So AC1 comma C2. Well, let's go down here and draw a picture. All right, so here's my X and Y axis. Let me draw a couple of vectors here. Here's vector C1. Here's vector C2. They form this parallelogram, right? Like that. It's supposed to be a parallelogram. It's kind of like a parallelogram. And some crazy arrows over my vectors here. Let me try to make a little better arrow. Like that. Okay. So that's the area. That's the area formed by C1 and C2. What if I like triple the length of C1? Right? If I triple the length of C1, there's another C1 and there's another C1. And I get this new parallelogram. make the colors match. So I get this new parallelogram, and in fact, there's a something like that. And so you can see this is 3C1. And the big parallelogram now, there's one big parallelogram made up of these three smaller parallelograms. And clearly that has area 3 times the area of the original parallelogram. So if I go back up here to this property, you can sort of adapt this to show for any scalar that the A kind of comes out. It's just, you can pull the, so it's the area of AC1, the area formed by AC1 and C2 is A times the area formed by C1 and C2. It also didn't matter that it was C1. Something similar would work for if you scale C2. So hopefully that's not too controversial. Okay. The fourth property is also comes, it has to do with this signed, the nature of the signed, that this is a signed area. It has a plus or a minus associated to it. And the idea is the following, because it's sort of, the order matters here. Because if it's sort of, we want to think of flowing, in these pictures that we just saw above, we want to think of flowing from C1 to C2. And if you turn sort of counterclockwise, it's a positive area, right? If this is a counterclockwise turn, then that's implies you have a positive area. Whereas if it's a clockwise turn, you have a negative area. So that actually shows that what you do, what if you happen to switch and think about the area formed by C2 and C1? Well, you just pick up a minus sign. That's the point. Draw that equal sign a little better. You pick up a minus sign. And so that's right, because we're just now, if we went counterclockwise from C1 to C2, then we just think about the opposite order. We're going clockwise from C2 to C1. This would now be clockwise, which would imply a negative area. Okay, so hopefully that one's not too bad. So basically, if you swap the columns, you end up with the negative, the determinant sort of swaps to negative. All right, and the last property is one that is a little bit, requires a real picture to draw, but let me, so let me go to a new page here, so I have plenty of room. And I want to think of what happens if you have the area, if you take C1 and you think of the area of that with C1 with C2 plus C3. So I have 3 vectors now. And I want to think about the area formed by those. So let me draw a decent sized picture here. And we can rotate pictures without changing areas. So I'm gonna make C1 just follow the x-axis. So there's C1. And C2, let's just say C2 is like this. And actually, I'm gonna have C2 coming out of C3 because I want to think about C2 plus C3. Say C3 is like this, right? Then let's see, then this vector from there to there is actually C2 plus C3. Right, and now I want to think about the area of the parallelograms formed by all these. So let me make some colors here. So we have the area, the one given above right here is the area sort of this big parallelogram. Just kind of draw over it like that. That's the area formed by C1 and C2 plus C3, right? Now, if we want to take, but if we think about it, we also have the area formed by, let's see if I can use a different color here. The area formed by C1 and C2 is this parallelogram. And, sorry. And the area formed by C1 and C3, well, remember this vector at the top here, at the top of this parallelogram is another C1, right? That's a C1 also. And so the area formed by C1 and C3 is, let's try purple. Let's see if that shows up okay. That's that parallelogram right there, right? The purple parallelogram. And the thing is, I claim that the area of the red parallelogram equals the area of the yellow parallelogram plus the area of the purple parallelogram. It's probably not that controversial, because parallelogram, especially if we since I made C1 sort of flat, then this is like the base, right? And the area of parallelogram is base times height. So that's like height one, this is height 2, right? And the red parallelogram has height 1 plus height 2. And so, yeah, so the area of the red parallelogram equals the area of the yellow parallelogram plus the area of the purple parallelogram. But like I just said, the area of the yellow parallelogram is the area formed by C1 and C2. And the area of the purple parallelogram is the area formed by C1 and C3. And so let me just get the color scheme correct here. This one was red. This one was yellow. This one was purple. And so that is a true statement. And I guess similarly, you could say, it's hopefully not too controversial to say that if we put, especially because we know we can sort of switch the order and all we come up with is a sign difference, that if I put it like this, C1 plus C2, C3, that area, that would be the area formed by C1 and C3 plus the area formed by C2 and C3. Okay, so those are the big properties that we're going to use to derive a lot of determinant properties. I do want to say that, so a couple more comments. The two comments are, there's one, we call it comment A. That's first, I claim that if you used row vectors instead of column vectors, everything still works out the same. This is a little bit hard to justify. You gotta have to get into some deeper math stuff, but if we go actually all the way back, let me go all the way back to the original. This picture on the up here is how, this picture on the right that shows the determinant. Notice that, well, a formula already. I mean, there's this sort of formula AD minus BC, right? And you sort of realize, oh, if I called this AB and this CD, then that doesn't actually change the formula. It just changes B and C's location. And so that actually turns out not to be a problem. So if we wanted to think of the area formed by the rows of the matrix divided by the columns of the matrix, that would work out the same. And then all these properties would also hold. So that's the point down here I wanted to make. So maybe I should say if we use row vectors from the matrix instead of column vectors, all the same properties hold. So we can do these manipulations to rows or columns, which is going to be very important. The second thing I want to say is that all of these properties generalize up dimensions. You can sort of try to think about these in 3D. But as an example, if we had the volume formed by V1, V1 and V2, so the same vector twice, that would actually be 0 because you're not really forming a 3D object with you really just have two vectors. You'd really be forming a parallelogram again in space, which has area, but it has 0 volume. So if we have a repeated column, a repeated row, means determinant is 0. And it turns out there's all these generalized that if you scale one vector, it scales the entire volume, right? If I had the volume of like 2C1, C2, and C3, that would be twice the volume formed by C1, C2, and C3. Okay, so in the next video, I'm going to show how all of these can be used to derive nice facts about the determinant, including a slightly different way to derive the AD minus BC formula. And we're going to see how that actually can be used to derive like the 3 by 3 determinant. Okay.